All right, hi everybody. My name is Dan Brancaccio. I work for Quanta Technology. My role there is executive advisor, which is just a term that kind of puts me in a hierarchy of a bunch of other advisors. Um, my background, I've been in the utility industry for over 40 years now. Started my career doing a lot of power quality software applications that actually looked at a lot of point on wave data from power quality meters and automatically generated reports on what it was finding in that data. It was a tool for engineers. Anyway, most recently, I've been involved with synchrophasers probably the last 15 years. I was the lead tech architecture design for the Western Interconnect synchrophaser program. So anyway, we'll start into this. Let's see. All right. Well, this whole thing is about, trying to get utilities to use cloud infrastructure. And, there's some pluses and minuses to that. And we'll go through some of that as we talk about this. I realize this is a forced oscillation group, but one of the things that people have been trying to do is get this data into the cloud, supposedly to reap the benefits of cloud computing. And you notice I use the word supposedly here because I think it's a lot more complicated than a lot of people think. Again, this is the standard stuff. I'm not going to read these slides to you. You can always read them later. But the bottom line is cloud computers are just a regular computer just in somebody else's building. I mean, that's the bottom line. There's nothing magic about these things. You can either get a cloud computer that looks just like a Windows server in your building on your own local area network, or you can get one that looks like a server that's part of a virtual machine, which a lot of utilities are already embracing. A lot of IT departments at utilities are building systems based on virtual machines. Okay. Again, a lot of this sounds like ads for cloud service providers, and that's primarily what it does. That's what it sounds like. Storage, databases, network, software, pay-as-you-go basis. And that's kind of the issue, the pay-as-you-go. That's one of the pieces that's somewhat appealing to IT departments at utilities, not quite fully appealing yet to the rest of the organization, but certainly the IT departments. Now they don't have to worry about patching their own servers. They don't have to worry about the 4 or 5 year hardware refreshes they have to go through. All this stuff now is owned by someone else, and then you're just guaranteed that you have these systems available for whatever guarantee you're asking for, 3 nines, 5 nines, whatever you want for your uptime. And this is a fairly good table that just talks about some of the things you can do with cloud servers, whether or not you are doing the virtualization, whether or not you're using software as a service. And all these terms here are just kind of identifying niche products that the cloud companies have kind of done this, right? Infrastructure as a service, platform as a service, everything is as a service, software service. All that means is instead of you paying for this thing once and putting it on one of your local devices, you pay monthly for it. So, software as a service. It's just like buying Office 365. You're buying software as a service there because you're paying for it once a year. It automatically is updated. You don't own it, and that's kind of where that comes from. And of course, now they've taken everything as a service. A subroutine as a service, as a function as a service, all these kind of things. And again, if you're on site, all these things are something that you manage or your service provider manages. You can look at the chart. All right. some of the definitions here are actually pretty good, and that's one of the things that I think we learned about early on at WISP when we started doing the wide area network for WISP, whether or not you were sharing infrastructure with other organizations or whether or not you had infrastructure that was specifically allocated for your use only. And that's really what this public and private cloud uh, delineation really addresses. If you're just setting up an Etsy page so you can sell your painted eggshells, you don't need to have anything private. You just have your stuff is just in a mix with 1,000 other people. The security is not that tight of a requirement. You just want to be able to take orders and get paid, and you can set up something like that. Private cloud is going to give you a little bit more security, but it's going to be more expensive. But now any hardware that is part of your cloud infrastructure is going to be solely dedicated to you. And of course, you're going to pay more for that. And again, hybrid and multi, kind of self-explanatory. And please, if anybody has any questions on any of this, please interrupt me at any point. All right, here's where it gets a little bit different. When we start talking about virtual machines versus containers, anybody who's been paying attention to what's going on in the computer world over the last 10 years, probably more like 15 now, understands this concept of containers. And all containers are basically very small virtual machines that run on something that are usually dedicated to a single task. So back in the Windows days, these were services, right? These were things like your SQL server. It had a service running on Windows so that anytime you wanted to talk to a database, you went through that service. Or for instance, if you were using any of the Grid Protection Alliance applications, like Open Historian, it had a service. Usually these are things that are running that do one task, and they're small, they're compact. If they blow up, they don't affect anything else on the system. That's really what containers are. And of course, they were initially only available on the Unix derivative operating systems like Linux. But now they're available on Windows operating systems as well. And it's just another way of isolating things. One of the things about containers that you have to realize is that you're typically limited to whatever the containers are that are available by the service. If you want to have your own container up there, that's something that you wrote, it's a little more complex to try to get that deployed. Most of these container systems are set up for well-known databases, for instance. I can tell you right now, there's no container service for running Open Historian available on any of these cloud systems. If you wanted to do Open Historian or Cygate or any of those Grid Protection Alliance applications, for instance, and I'm not sure about others like EPG, their ePDC, things like that, probably can't run in a container system. For that, you'll need a virtual machine. And a virtual machine, just what it sounds like. Again, it's just like having a server sitting right next to you in your office, except your connection to it isn't over a 10 gigabit LAN, local area network. It's through, basically an internet connection, whether that's a VPN for security or just a standard internet connection. You're now dealing with that server there. And of course, I think since everyone on this call is in the forced oscillation world, they understand what bandwidth limitations are when you're trying to move a lot of data. So those are the two types of things. Any questions about virtual machines or containers? Okay. I think it's kind of straightforward.
Dan, this is
Yeah.
Hassan. Good morning. Just because you brought up the question of container, I had a question, maybe relevant, but it is that the Docker, Windows Docker that be installed for some of the application. Is it a virtual machine? I didn't get the concept why the Dockers are so important. I mean, in terms of containing the app to just a certain, basically from security point of view, I understand that part of it, but I didn't think of them as a virtual machine. Are they virtual machine or no? It is like a service.
Yeah, it's more like a server. I mean, right. And you notice on the left here, they actually point out specifically virtual machines, and these things are all virtual. So some of this terminology is interesting to say the least. But yeah, that's also basically a Docker is a very small, and again, they use this term just to identify that it's small. It's a service, right? They didn't want to use the word service because everybody associates that with just your standard Windows operating systems. So they came up with Docker. And because you can have a lot of them running on a machine, just like you can have a lot of services running on a machine, and they can talk to each other, just like you can with services. So this is just, and again, started with Linux. It's there, and Linux or Unix, then Linux, of course, had things called daemons, which you don't see on here anymore, which was really the original name for a service on a Linux machine. Because always everybody has these concepts of you have computers running applications that somebody may be interacting with, and there has to be a lot of support things running on the system. Well, one of the goals have been in the computer industry for years is to try to make sure that if one of these support tools, a service, did something that it shouldn't do, it didn't crash the whole system. And so Dockers are kind of as people got smarter and smarter and smarter about how to run these things in a mode where if they blew up, they wouldn't damage the whole system or cause the whole computer to crash. They finally came up with this name Docker, which meant that it was, as self-contained as possible. And I can guarantee you that there's Dockers out there that can crash the whole system, but it's far less likely than it was, 20 years ago when you'd get the blue screen every time, somebody tried to load a bitmap that was too big. So that's all they are. Again, nothing magic about these things. Kubernetes is a way these things can talk to each other, the way they can. That's one of the other things that happened as they started getting these things isolated. They wanted to make sure there was a way to pass your authentication for a user to be able to interact with any of these things. So that's what that is.
Okay, thank you.
Okay.
Thank you.
And as you can see there, potential security risk if not managed properly. Everything's a potential security risk if not managed properly. Okay. Benefits and opportunities. Okay. And here's one of the things, concern data security and privacy. I'm just going to focus on that because I was recently working on a project with PNNL where we were discussing, data sharing. Anybody who's struggled over the last 10 or 15 years to get synchrophaser data from some utility that would like to do analysis on it or try to write an application that would do something with it, or just wants to look at it to try to determine maybe some event occurred and try to determine what happened, knows that sharing the data is always a problem. So security and privacy, as you know, NERC is involved with a lot of this data security. And one of the stumbling blocks has been for years for utilities starting to look at using the cloud, basically, again, a computer that's not physically in their facility, is just that. People understand that we have electronic security perimeters and physical security perimeters that NERC requires for devices. So while we may be able to move data up there for analysis, we have to be very careful about moving data up there that may be used for either A, decision making, or B, may be data that there are concerns about access to it. And even though, and here's kind of the double-edged sword here, even though there's a very good chance that the security and privacy of the cloud systems are better than the utilities' own physical servers that they have in their buildings, even though it may be better. In fact, a couple of years ago, one of the CEOs of PG&E, I can't remember which one it was, said she can't believe that their security is any better than, you know, Amazon's AWS systems. But the problem is some of the NERC requirements, if you look carefully through all the NERC requirements for this, some of them say that anybody who has access to these machines has to undergo NERC training at the utility. Anybody who's ever worked for a utility on sensitive data has had to go through their training. Anybody on this call that's had to do that knows they have to be trained up, take those NERC classes and get authorized so that they can look at the data. I've had personally to take them for like 6 different utilities. So I know that that's there. And so now you run into this issue where how are we going to get, you know, AWS people to take all these tests to make sure that they're compliant with the NERC training? That's where it really gets into. It's not so much the actual physical security of these things. It's all the additional paperwork really that goes on to meet these NERC requirements that makes this a stumbling block. So those are kind of things, and it's, again, not on this page because people don't really dig into it that far ahead. And frankly, if it wasn't me giving this presentation, you probably wouldn't even hear it. Okay, again, these are all the pretty much, you know, benefits and the concerns. Change management's down there, that kind of touches a little bit on what I was saying, in skills and gaps training. Okay, potential. Okay, when I first got this slide, the word potential wasn't in there. So just so you know, these are potential applications for cloud-based systems. Again, there's a lot of hurdles to jump over before you're going to be able to do this, right? You know, things like virtual power plant control, right? GIS system. GIS is probably a good place to put this, because most GIS systems are already kind of browser based. You already use a browser to interface with the GIS system, and they do have a lot of data, but it's not like you got to push a lot of data back and forth to the cloud to do this. You know, you have somebody there configuring the GIS system, maintaining it. The bandwidth requirements for that are low, and then you have other people looking at it with their browser. This is a perfect example of a good solution to push up into the cloud, because now, again, with your two-factor authentication or multi-factor authentication, anybody can look at the GIS system with their corporate laptop, even if they're at home. They can do that. They don't have to be on site to do that, although thanks to COVID, there's a lot of ways to get around that limitation as well now. Most utilities have ways to remote in with VPNs, even if you're off-site. But again, that's a good use for it. Again, outage management systems, also possible good use. This is not NERC data, so you can you know, this is something that would also look good for that. Again, not a lot of high bandwidth usage for that. It's not like something where you have to push constantly 60 reports per second data, 5.2 million measurements a day for that. Demand response management, now we're starting to get a little bit more where it's going to be a little more difficult for that. Anyway, but here's obviously some potential applications. Anybody see anything on here that you think is missing, or questions about anything in general? Okay. All right. So now we run into our first one, bandwidth issues. And I think it's a little bit later in the slides, but we set up a lab. I'll talk about that when we get to it. Anyway, so utilities right now are using a few different techniques for sending synchrophaser data internally, right? They're using microwave, leased lines, high bandwidth, MPLS networks, things like that. and they're handling it pretty well. It's a struggle depending on the size of the utility. I know some utilities are still using 1.5 megabit T1 lines. I mean, literally twisted pair copper. AT&T doesn't even want to support it anymore. They're paying 3 or 4 times what it originally cost to deploy that. The utilities are, only because it's just too hard to switch out. But they're gradually putting in things like 10 megabit MPLS internally. Okay, and that's the struggle. Now, one of the things you could do to avoid some of that is to do wireless internet, right? In other words, go right from your physical substations to the internet. And by wireless internet, we're talking about things like Starlink and all those kind of things. But I can tell you right now that those things, and again, this is on utility scales, the challenges are different. Might be expensive to put these things in place at substations, but the cost of changing out to an MPLS network may be more expensive. But as we know, as soon as you start doing this, all of a sudden these cloud systems start to get a little bit less appealing when you start pushing a lot of data up to it. Okay. EMU data management, direct sensor to cloud streaming. Okay, that's the innovation. And we've actually tested that in the lab, and it does work. Because if you're looking at a single substation, even with, say, 10 or 15 PMUs, the bandwidth is still kind of reasonable, even at 60 reports per second, with, say, a couple hundred signals going up in a data frame. You can still do that. And it does deploy faster. You just pop an antenna on the roof and you're done. Right. Storing the data, though, then becomes expensive. And I can tell you one of the things that people really don't talk about until they start looking at this. When you're talking about terabytes of data that you want to store in the cloud, whether it's, and usually now we're talking virtual machines, it gets pretty expensive pretty fast. But again, it's all out of your hands. You don't have to worry about it. Nobody has to manage it. Once you set it up, you can say you want it backed up. You can say you want it backed up offline. You can do whatever you want. Of course, it's whatever you want with the dollar signs. But it does have some benefits. Okay. So this is one of our lab setups that we did at Quanta. We had a couple PMUs, switch, and a firewall. We used initially a LTE modem, only because it was taking forever to get us a Starlink connection from our lab. And not just from Starlink, it was also internal security concerns at the company, and it had to go through a lot of approvals. So we started out with an LTE modem, and frankly, an LTE modem really was pushed to its limit just to handle 2 PMUs. It was actually dropping quite a bit of frames. We were using the spontaneous mode, UDP spontaneous, out of the PMU as a way to isolate the signal going out, so we didn't have to worry about anything like that. It was going over a VPN, so it was encrypted, and we had that up to we were using Azure in this case, and then we were using a virtual machine, and we had a bunch of Open Historian products on there, and that actually worked fine, and that allowed people sitting anywhere with the right multi-factor authentication to log in and use the interface supported by Open Historian, Grafana, to look at data and look at all the synchrophaser data. Like I said, this worked fine for 2 PMUs. We are in the process of switching over to a Starlink connection to see how much we can push through that. Any questions on this architecture here? Okay, it's pretty straightforward. And this just says what we put it, our lab wasn't a substation, but we did this because we wanted to use this as a test to how to get basically at a utility with little to no infrastructure, and there are some out there, and try to get PMU data streaming from a substation to a control center. And in this case, just for post-event analysis, archiving, planning, not for any, initially anyway, not for any real-time control or even real-time wide area situational awareness, only because of some of the latencies that we ran into. All right. So again, obviously you got to have a real time of day clock, accurate clock in the substation. You got your PMUs, and they're going to be, in some cases, in a relay or a DFR. We have switches in there and a firewall, right? And a VPN router. The VPN router is at the edge. So prior to pushing the data onto the internet, over something like Starlink, it's encrypted. And then at the other end, you would actually have to decrypt it. Okay. And of course, everybody's complaining about, anti-spoofing, GPS clocks. And there are ways around it. One of the simple ways around it is to also bring PTP out to the substation. But again, if you don't have enough network going out to a substation, excuse me, to get synchrophaser data, it's unlikely you're going to having a network infrastructure out there where you can deliver PTP as well. But again, outbound traffic only. That's one way to set this up. There's no need to have any firewall set up for any inbound traffic. Makes it a lot easier to set up those firewall rules. You can just block all inbound traffic. That actually makes life a little bit easier to manage the security. All right. This is basically just the pieces from the drawing that you saw prior to this. Any questions on any of this stuff? Okay. All right. Again, a little more detail. Now, some of you may know that with a tool, that Grid Protection Alliance, or a more recently developed protocol for delivering synchrophaser data, the IEEE 2648, I can't remember. Anyway, it was the STTP. Can't remember what the IEEE number is now. It's pretty new. That actually has built-in encryption, so you can use that even without a VPN to encrypt the data. The application itself does the encryption, and then the application at the other end, on the receiving end, compliant with STTP protocol, can do the decryption. This makes it a little bit easier because VPNs are typically another added cost. But again, we used a VPN here because at the time, that STTP hadn't become a fully accepted IEEE spec at that time. We're using Grafana based. Grafana is a very nice tool for visualization. As you know, there are other vendors now coming out with synchrophaser visualization applications, like Schweitzer, for instance, that are also browser based. So once you set them up somewhere, you can just use your web browser to look at the data. And that would be another example of something you could do. Although I don't know yet if Schweitzer has a cloud-based solution for sync wave operations. It may be, if not now, I'm sure it'll be soon. Okay. Again, hopefully this is informative. I know everybody here is mostly looking at forced oscillations. All right. So our results. Again, we had 2 relays. We had a Schweitzer 2488 clock, some hardware we had there. Again, basically just tells what we did to get this set up. The VM was this a machine, which means it was on some much larger computer. And what we got, and this is just like a VM in your own local utility, you get a very powerful, 128 core multi-gigabyte memory machine, and you use a part of it to do this work. And on Azure, and the machine we set up was a basic Windows Server. I think it was Windows Server 2019, right? 32 gig of RAM, 8 cores, and a 2 terabyte hard drive. And I can tell you that if that was a standalone machine, and I have these basically these exact same kind of machines at other utilities that are getting data from 200 plus PMUs with no problem. With only the 2 PMUs that we were sending, this was pushing this server. So these VMs have to be scaled a little bit higher than you would think when it's a standalone machine. And I mean, this is just basically the nature of the beast. There's no magic here. You got one giant computer acting as 20 smaller computers. Even though the specs look like that would be sufficient, it's not going to have the same performance as a standalone computer with that same performance. And frankly, I don't care what the VM people tell you. That's just the way it is. And a lot of times when you talk to the VM proponents, they go, well, it just needs to be tuned up properly. Well, by the time you get it tuned up, you basically are taking over the entire virtual system that supports this virtual machine. Okay. So Open Historian, in this case, we were using it for 2 things. One was to archive synchrophaser data, and then another slightly less common use, and I'm not even sure how many people are aware that Open Historian can do this, but Open Historian can also track statistics on the data that's coming in. How many data frames from this one PMU did I receive the last minute? How many of those had time errors, or how many of those had data errors or data invalid flag set? What was the latency over that minute, min, max, and the average latency? It can track those, and you can build dashboards in Grafana to actually look at those KPI values. Here's kind of a look. This shows the received counts, and you can see, you should be getting 3,600 every minute. And in this case, you can see it was fluctuating a little bit. You weren't getting 3,600 every minute, but at least the data errors and the time errors were all down in the zero. That happened to be the name of the PMU we had in the lab at the very top. And you can see here's some of the latency measurements that you can see. Now, latency measurements, and this is something that probably is in addition to just how virtual machines work. This is one of the important things I've been discussing a lot, especially at my NASP meetings. If you want to get good latency measurements, cloud or no cloud, doesn't depend, doesn't really matter. You have to have a good time of day clock at the server that's receiving this data. If you want to know your full latency from the field to the system that's consuming this data. And that's not as easy to get as you may think, right? Everyone's probably heard of PTP for network time protocol. That's accurate to the nanosecond level. But there are a lot of servers out there, including these cloud servers, that don't have access to that. That's one of the things that we weren't able to get. And in some cases, and it's not, and it's very important that the server knows exactly what the time of day is, because that's what it's comparing to when it reads that data frame coming in on a PMU or synchrophaser data frame. That's got a timestamp on it that's accurate plus or minus 50 microseconds. If you want to know what the latency is, you have to know what time of day it is accurately on your server. And in some cases, if the server is off, it will look like that data came from the future, or it will look like that data is, 5 minutes old, when really it's milliseconds old, because it's not uncommon to have a Windows server, and 5 minutes is maybe an exaggeration, but I've seen them 30 to 45 seconds off on the time of day clock on Windows Server. Very common. And so now the data looks very old coming from the field. And in fact, if you're setting this up for real-time solutions, you got to be careful what you set your local consumer up on when it's going to accept or not accept data. Now we're getting a little bit off the cloud stuff here, but I thought I'd throw that in there because it's something that I've been dealing with and discussing at NASP. Okay. Now here's one of the things about cloud computing, right? They say, okay, once you get all this data in the cloud, now you can integrate it with existing AI or machine learning tools that are in the cloud. And yes, this is correct. That's kind of the big push. Nobody wants to set up a system in their utility with 1,000 GPUs in it to run their own AI, on these things. Again, I think there's a lot of hype involved in AI and ML, but if you want to experiment with it, the cloud is certainly a place that you can do that. I know, I'm not sure if anybody's on this call from Dominion. I know that those folks have been doing something with cloud work in the past, over the past couple of years, and they can probably give a slightly better idea about this. But yeah, that's one of the benefits. Now, do you need to have real-time streaming data going up to the cloud to do this? Probably not. So there may be less expensive ways to get your data up there. But all in all, at some point, it's going to require moving a lot of data. As we all know, we're talking, gigabytes a day of synchrophaser data from any decent installation of PMUs at a utility, terabytes a month. And that's still a lot of data to move into the cloud. But that's certainly one thing that's a lot easier to get access to is these machine learning and AI tools that can look at that very large data sets. Okay. And I really didn't talk about point on wave here, but as you can imagine, point on wave is going to require even more bandwidth, unless we're talking about just point on wave during pre and post event, 5 minutes worth of point on wave data or 10 minutes worth of point on wave data, then that's a whole different ballgame. And frankly, I think in the utility industry, that's going to be more likely to be how we first step into using point on wave data. All right, I think this is the last slide. I'm going to go to the questions and comments. So there we have it.